So today we're going to talk about caches, and as you will notice throughout this course, caches is one of the most common tricks of the computer architects to try to get more performance. If you look up the word cache in a directory, or a dictionary, you would find a description like a secure hiding place, secure space of storage. But as you also will notice during these lectures, this is not a very safe place. Cache is a place where data may live for a little while, it may be bumped out, and it could actually be quite complicated to reason about exactly which piece of data may reside in a cache at a given point in time. This lecture will focus on how to use cache techniques to move data from the slow and boring memory far away into a location much closer to the fast pipeline, and more specifically to try to make that cache design fast enough that it could work on par with the speed of the pipeline. So we're down in the nanosecond or fraction of nanosecond game in these lectures. Later on, we will talk about other techniques where you could, for example, turn the entire memory into a cache, such as virtual memory systems. So, of course, cache knowledge is useful when you design a computer, but it's also, as you will see later on, very important to understand when you would like to write optimized programs, or writing a compiler, or for that matter, to get an operating system to work at all. We really have to understand how the caches work. There are other places than a computer architecture where you use caching techniques. So web caches, proxies, file systems, and so on are also examples of caches. And some of the techniques we talk about in this lecture could also be applicable there as well. As we've already seen, there is a deep memory hierarchy in computer architecture, going from things that, like registers that reside very close to the ALU and the pipeline, to SRAMs that may be fast and reside close to the registers, SRAMs that may reside further away from the register, but still maybe on the same chip. We could have the DRAM even further away, and disk, of course, is furthest away, and so there is a speed and capacity difference between all these different levels in the memory hierarchy. Back when computers were new, it was the task of the programmer to move data from one level to the next in the memory hierarchy. So, for example, explicitly say, move this chunk of data from the disk, put it exactly here in memory, and then use physical addresses to access exactly those memory locations. For many practical reasons, we don't do that at all these years. We instead try to come up with a transparent way of moving the data in the hierarchy. So it's the virtual memory system that moves the data into the DRAM. It's the caching system that moves the data from the DRAM into the SRAMs of different levels. When I look at that cache hierarchy of today, it sort of reminds me of how it was back in the 90s when you wanted to make a telephone call. Okay? So if I wanted to make a telephone call to the world, the 4 billion people out there, I simply hardly knew how to do that. You have to get in contact with some kind of international telephonist, and it could take maybe half an hour to pull that number out, and it was very complicated. If I wanted to call somebody in Sweden, I would call the number service, talk to a real human being, tell the name of the person I wanted to talk to, and get the number back. So here I could reach maybe 8 million people, and it took me maybe 2 minutes to get that number. If I wanted to call somebody in my own city or my own province, I had a telephone directory at home, and I could do the lookup manually in that directory, and maybe that took about 30 seconds or so. And of course, you also kept some piece of paper next to your telephone where you wrote down the recently called numbers. You didn't have to go through this process all the time. And more specifically, the notes you had next to your phone often was organized like an address book. And the way we organize that address book is very similar to how we organize caches in computer architecture. So let me first go through an example how that telephone book worked. So that telephone book had two features. One feature was an indexing function that quickly let us reach the right page of that book. And the other feature was the data field, where we wrote down the name of the person we wanted to call as well as the telephone number. So the telephone number here corresponds to the data in the cache, and the name of the person is the identifier of that piece of data. So in this example here, I assume that you can only have one person's name on each page. So this is an address book where you can remember the telephone number of 28 people if you use the Swedish character set, because that's how many letters we have for the index function. So this is a direct map cache with 28 entries. The way you find a person's name is you typically use the first letter of a person's last name. Actually, in this example, I use the first letter of a person's first name, Tommy. You use that letter to index into the right page of that book, and then you store the part of the person's name you didn't use for the indexing on that page. Of course, we don't need to write the T, because any name on this page would start with a T. And you use that remaining tag that was stored in the telephone book, and you compare it with the part of the name you didn't use to index. If there was an equality between them, then you declare success and you call that number. However, if you called some other person's name, so for this example, Thomas, we still index to the T page, and then we compare Omi to Umas, and turns out they are not equal. So this is a cache miss. So that means we will have to look up Thomas' number in the telephone directory, or call the number service, or wherever Thomas resided in the world. Now we could replace the entry on that page in the telephone book to instead have Thomas' number Umas and Umas' telephone number written on that page. And this is how the cache replacement worked in our scheme. Trivial replacement, since we only could have one person's name on each page. It was also easy to determine who which information we should overwrite when we entered a new information into that book. So this is called a direct map cache. So this is exactly how you, for example, can implement the cache. So the cache, of course, is not an address book. Cache is a place where you store some information that resides in memory, but it's organized like an address book. So you could store, remember, some memory or some address identifier that identifies a place in memory in the address book, and you can store the data that's associated with that space in your address book or in the cache. So you use an address as a lookup. You compare part of the address with this address tag that we store in the cache, and if they are the same, then this hit signal will be asserted, and the data being returned to the CPU could be trusted. If it's a miss, then we have to go all the way out to the next level in the hierarchy, so memory, for example, to get the data. And once we got the data, we probably updated the address book as well. But this is really how a direct map cache would be implemented. Well, you have an example here of a 4 kilobyte direct map cache with capital B in computer architecture typically refers to a byte. So that's 8 bits of data. When we do a lookup in the cache, we're going to use a 32-bit address, and the 32-bit address in computer architecturally is typically byte addressable, which means that it identifies a byte within memory. We're going to use some ordinary memory, fast memory, called static RAM, SRAM for short. So this is just ordinary memory. We're going to figure out how many entries we need in that SRAM memory. In this example, we store 4 bytes together, because it's we want to present 4 bytes of data. A word is 4 bytes in this example, so we want to present 4 bytes to the CPU, and so we store 4 bytes of information here. That means we need 1K entries to store 4 kilobytes of information. Use an index function to select exactly which of these 1K entries that we would like to look at. This is similar to the index function of the address book. We choose one of the possible locations. since this index function must find 1 out of 1k possible entries, we will need 10 bits of index function. So the index function will let us find the right place or the right entry out of those 1k entries, and the information stored at that place in the SRAM will be read out. So we will read out the 4 bytes of data. We will read out the address tag, which is the one we're going to compare with to figure out if this is the right information. And we're going to have a valid bit saying whether or not we actually can trust this data on that entry in the cache at all. So what is a good index function? So we already said that we need 10 bits of information, 10 bits of address as the index function. So we're going to choose 10 of these bits as an index function. And the question is, which bits would be most appropriate to use as an index function? And as a hint, let me tell you about a stupid index function. So the index function we used in the good old address books, where you use the first letter of somebody's last name as an index function, is probably the worst index function you could think of. In my example, my name is Hägersten, which meant that all my relatives end up on which page? They end up on the page, the age page. So in my address book, I had an overpopulation on the age page. So anybody starting with an H had a hard time to be remembered in my book because all my relatives were there. While other pages starting with Z or with X, for example, I hardly didn't know anybody back then, starting with those names, those pages would be empty. So that was a very bad index function. So we would like to find the index function that makes us equally use all these 1k entries of this book. So the question is, which of these address bits would we choose as index functions? It turns out that the least significant address bits are the ones that are going to change most frequently and going to have more or less a random access pattern, while the most significant bits may change very frequently or not at all. For example, if I only have a partly populated memory in my machine, that means that the most significant bits of the address would never change, which means that if I use them as my index function, then I would only use one of the entries in my cache. So we would like to use some of the lower, least significant bits of our address as the index function. So, however, the last 2 bits we will not need to bother about at all, because the last 2 bits, as I said, this 32-bit address identifies a byte of information in memory. And since our job is to provide an entire word to CPU, we don't care about the value of the last 2 bits, because that would help, but that would just identify which of these 4 bytes the CPU is interested in. So that is a task that the CPU internally will take care of itself. The task of the cache was just to provide a word to the processor, to the CPU. But we use the next 10 bits. So we toss away the lowest 2 bits because they identify a byte within a word, and then we use the next 10 bits, 10 because we need to uniquely identify 1 out of 10k entries, and they are our index bits. The remaining bits of the address we're going to compare to the address tag which is stored on that entry in the cache. So it's going to be a comparison between 20 bits of the address we wanted to look up and 20 bits of the identifier stored on that location. We compare them, we make sure, so this is a comparator comparing 20 bits with 20 bits, and the one that comes out here is the one signal will contain 1 if it's a hit, and it contains a 0 if it's not. Then we also make sure that the valid bit is set, and that is what we use to produce the hit signal, telling the CPU whether or not these 4 bytes of information can be trusted or not. So the memory overhead here, counting how many useful bits, these are the useful bits stored in this cache, compared with the useless bits or the overhead bits, the address tag and the valid bit, is 21 over 32. So that's a memory overhead of 66% for implementing this cache. Latency for going through this cache is the latency for doing a lookup in the SRAM, the time between we put the 10 address bits as the index function into the cache until the data stored in that location comes out, plus the time to make the comparison, plus the time to make this little AND. And I should highlight here that This may not be exactly how the caches are implemented. There can be tricks. We'll discuss some of those tricks later on, but for this simplistic picture of how you implement the cache, this would be how you will get the latency of that cache. So here you go. We designed a cache. It has a functionality. You provide an address to the cache. It will provide a data word back, and it will provide a hit signal telling whether or not this is a hit or a miss.